also remain unchanged. Okay, great. The recording has started. Awesome. Okay, sorry. The other attributes that you're not interested in changing, they should be preserved. So an example of this would be machine translation, which I'm showing in this figure on the right here. Suppose we wanted to translate from Spanish to English. Then what we would like our model to do is when presented with a Spanish sentence, for example, el perro corre, we would like it to translate that into the English equivalent, the dog runs. So in this example, the attribute that we are changing is the language, specifically from Spanish to English. And the other attributes, in this case specifically the meaning, we want to keep that preserved, okay? But we can generalize this notion. For example, formality transfer. Suppose we have an informal English here, where are you, with abbreviations, no capitalization, and all lowercase, and we'd like to formalize that by capitalizing, adding punctuation, and spelling out the words fully, okay? So these are both examples of text rewriting tasks. Now, how would we go about training this? Well, in general, you would use what's called parallel data. So this is called a supervised approach. The title of my thesis says with missing supervision. Well, this is what supervision is. So normally what you would do is you would pay a human annotator or a team of human annotators to prepare input-output pairs, examples for what you want the machine to do. And this data we call parallel data. So using, again, Spanish to English machine translation as an example, perhaps I would prepare, I would collect a number of Spanish sentences, and I would pay bilingual annotators to translate them into English. And then I would present my model with these pairs of the Spanish inputs with their corresponding English translations. And I would train the model on it. Now, modern methods, it's actually pretty straightforward to train a model to do this in the presence of this data, to produce these outputs in the presence of these inputs, and to generalize that so that you can, with reasonable performance, perform Spanish to English translation. The problem is that for most modern approaches, specifically neural networks, they require millions of these examples in order to get decent performance. And this is a problem because it's very expensive to create this data. And so for many settings, it's actually infeasible to do this. So how could we get around that? Well, one other type of data that we may be able to use is called non-parallel data. And you may hear me refer to this as monolingual data, specifically in the context of machine translation. So in this figure here, suppose I have some Spanish sentences, and I also have some English sentences, but they are not translations of the Spanish. In general, they may have nothing to do with the Spanish. This kind of data is much easier to collect because I can just get it from the web. I can go visit a number of Spanish news sites, download some articles, and do the same with some English news sites. So data of this type, it's very easy to collect large amounts of this data at very low cost. But the technical challenge is figuring out how to find a correspondence between your source and target. In this case, the source and target languages, right? It's like, how do you train a model to perform, in this case, Spanish to English translation, if you've never actually shown it a specific example of a Spanish input and an English output? And that's one of the things that we're going to explore today. So we're specifically going to look at three types of text rewriting task. The first is called bilingual lexicon induction, which is basically machine translation of single words or phrases. And the setting we're going to consider is one in which we have no parallel data, and we only have monolingual or non-parallel data in each language. The next tasks we'll look at is machine translation, which is translation of full sentences in this context. And the setting we'll consider is where we actually do have some parallel data, but it's of the incorrect type. As an example, you can imagine instead of Spanish to English, maybe have Spanish to French and German to English as an example, in addition to some monolingual data in each of the languages that we actually care about. And the third task we'll look at is style transfer, which is pretty broad. One example of it is formality transfer, which I had on an earlier slide, making something more or less formal. And for this setting, we'll assume not only do we have no parallel data, but we actually only have one unlabeled corpus. We don't even have separate non-parallel corpora with labels. And I could consider a few other things in the thesis itself, but I'm going to skip over them for this talk in the interest of time. So let's dive into the first part of the talk on bilingual lexicon induction. So This is the task of producing a translation dictionary for a source and target language that contains the translations of single words or short phrases. And in general, this is the, most often the best translation of this. So as an example, you're taking Spanish to English again. Suppose I have this Spanish word. We would say that in general, the best translation of it is dog. And for casa, it would be house, okay? Why would you want to do this? This can often be used as a sort of first step towards translating full sentences in the context for machine translation, right? Once you figure out these word and short phrase alignments, it can be easier to do more complicated translation. Now, there are a couple of different approaches you can use to do this. The broad class that I'm going to consider here deals with word embeddings. So word embeddings are multidimensional vector representations of words. What does that mean? Well, let's look at this, this figure here, okay? Suppose I have this 2D space, all right? What I want is I want every word to show up somewhere in this space, and I want similar words to be close to each other, while dissimilar words are going to be far apart. And the way that we can do that is for our language, say English, we're going to put all of the words in just a completely random place within this space, okay? And then I'm going to take a large collection of English data, just text, and I'm going to repeatedly pick a random English word, and we're going to look at the words to the left and to the right of that word, and maybe 2 or even 3 to the left and right. And that collection of words, I'm going to find all of them on my space, and I'm going to move them all closer to the original word that I picked. And then I'll pick some random other words and move them farther apart. And I repeat this process millions and millions of times. And what we get out at the end is exactly what we want. It is this space where the similar words, i.e. words that show up next to each other a lot, are going to be close together, while dissimilar words or unrelated words will be far apart. Now, another interesting property of these word embeddings is prior work noted that if you perform this process for multiple languages, suppose English and Spanish again, they tend to be isomorphic. And by that I mean that there's a correspondence there. And I think this is best illustrated with this figure. So what this figure represents is actual, it's a 2D simplification, but it represents actual word embeddings for 5 animal words in both English and Spanish. All right. And now if you look at these, the axes are different, the numbers are different. I'm getting
Parker, you're muted, and James, you are unmuted. Parker, I think you're the.
Yeah, I think I'm unmuted now. Can you hear me now?
Yes.
I did not press it. Maybe somebody. I don't know. What was the last thing I was audible for?
I think several people are unmuted. Dan, you're unmuted.
Okay. Yeah. Everybody, please mute yourselves.
Thank you. Okay, so you were talking. Well, it was only very, very shortly, Parker. You can pretty much pick
Okay.
up.
Okay. Sure. So, looking at this figure here with the English and the Spanish, you see the number, the axes are different, the numbers are different, and they're not exactly the same, but you can see the same basic shape is present for these 5 words in both the English and the Spanish, such that if I hid these labels and suppose you don't know Spanish, you could look at this image and you could figure out that the translation of cow is vaca just by looking at the shapes of this collection of 5 words, right? Which is a very cool property. However, we actually don't get this for free. So the word embedding process is randomized, and so it might not look so clean as this right at the beginning. And so to get this figure, what they actually had to do was apply a linear transformation, which just means they had to take one of the spaces and rotate it and like stretch it a little bit in some of the dimensions to make it line up like this, all right? So the task, so we can use this for bilingual lexicon induction. We just have to figure out how to do that rotation and stretching, i.e. a linear transformation. So for this project, I extended some prior work that does this from Arteche et al. In 2017. They propose a framework for learning this sort of mapping. And so in this figure, so they start out with a dictionary, which is a bilingual lexicon, with some correspondence between some source and some target words. Now, you may think that sounds a lot like parallel data. I thought this was supposed to be unsupervised, where we didn't have that. And you'd be right. However, it turns out that we can actually automatically infer a small but high precision dictionary just using numerals. So that is, we will assume that the number 1 in English, like spelled with the digit 1, is the same as the digit 1 in Spanish. Same for 12 and 365 and all of the numbers that we find in our data. We will assume that they correspond to each other, right? And so in that way, it's not, it's minimal supervision because we don't need to pay somebody to come up with these examples. Now, in this diagram, these two spheres, X and Z, represent our source and target word embedding spaces, which are these complicated multidimensional spaces. And for this simplified example, we'll pretend that our X language just consists of numbers, and our Z language just consists of letters. Now, in these diagrams, the white ones, those correspond to entries in our dictionary. Our dictionary tells us that 1 lines up with A and 2 with B, and so on. So what this system will do is it will learn a transformation, rotation and scaling, that will superimpose X on Z. So if we look here, when we superimpose them on each other, we see that the ones in the dictionary, they are close to each other. And that's what the system is trying to do. And based on the result I had from the prior slide, we also see some other pairs that line up to each other. They weren't in the dictionary before, but now we see X and 4 and Y and 5 are close to each other. And so we'll infer that they are actually translations of each other. So we add those into our dictionary and then actually repeat the process. With this new expanded dictionary, we do the mapping again and we repeat, and this tends to get better over time and will eventually converge. That is, it'll stop finding new pairs. And this system is pretty good, especially considering the fact that there's no parallel data involved, but it does have some problems. So I've got some examples of that here. So in all these cases, we're going from English into some other language. All right, and so the English word that we're trying to translate for this first row would be unevenly, and this baseline system came up with this German word, which is actually the antonym. It means evenly. And here's what the reference should have been. And my favorite example here is the second one, which is where the English word Ethiopians, referring to people from a specific country in Africa, just got translated as Africans, which is, at worst offensive and at a minimum makes the model seem uneducated, right? So there are definitely some problems here. But the question is, why does this happen? The reason this happens is because word embedding methods are really good at separating completely unrelated words. But certain types of words, including antonyms, that appear in similar contexts, they cluster together, and it's difficult to make these fine-grained distinctions between them. So for this baseline system, it can have difficulty figuring out which one you mean. But something I want to point out here is that in each of these 4 examples, if you compare the second column, the input English word, and the fourth column, which is the reference that we should produce, there's a hint in the spelling. So in the first example, this UN prefix exists in the English and the German. And for the word Ethiopians, that Theopi part is present in the German as well. And these other 2 examples have similar correspondences. And so what we wanted to do in this project was to leverage this spelling or orthographic information as a signal to do this
Okay,
lexicon induction.
I have a
Yes.
question. Are you
Okay.
making an assumption that the languages are, from the same root, like in the tree of languages? Okay.
That is an excellent question. Spoiler alert, this technique works better for related languages. That's an excellent question. So German, Italian, and of course our source English are all in the same language family, but Finnish is from a different language family. So we will see some results later of how well we do there. But great question.
Thank you.
Yes,
Okay.
thank you very much. I would like to ask everyone to hold their questions till after the presentation is over, then we'll have time. Thank you.
Great. Thank you. Okay. So moving on. So again, we want to use spelling information as a hint. We proposed 2 modifications to this baseline system. The first is very direct. We tell the model, if a source and target word are similarly spelled, they are more likely to be translations of each other. And the way we do this is when the system learns this mapping and when it's trying to find nearest neighbors, close source target pairs to add to the dictionary, we're actually going to modify our distance metric and push source target pairs closer together if their spellings are similar. And we use edit distance to do this. So this is very direct. The second method is more hands-off, where we simply expose spelling information to the model and ask it to decide whether there's any useful signal there. And so what we do is we just extend the dimensionality of these word embeddings with character counts, basically. So suppose a very simple example where our embeddings are two-dimensional, and suppose that the only letters in existence are A and B. So if we started out with the word ABA with this simple embedding, this random embedding, what we do is we would augment it by adding two additional dimensions, one for the letter A and one for the letter B. And the entries for A, we would just count how many A's there are and put in that many, 2 times a constant. And there's one B, so we put 1 times a constant as its position along that dimension in this augmented space. And then we run the system as is, and it figures out how to map those dimensions in addition to the embedding dimensions to figure out the correspondence. And these are the results of doing that. So in this figure, the y-axis is transfer accuracy, how often you get the translation right. We experimented with 3 language pairs. English was always the source, and we experimented with German, Italian, and Finnish as the target. In each block, the blue column on the left is the baseline system, followed by our edit distance, the very direct method, followed by our embedding extension method, which was the hands-off exposing character counts. And those methods are actually independent, so we can do both, and that's what the 4th column represents. And so what I'll note is, first of all, we universally outperform the baseline, which is great. We'd get the best performance by doing both of these methods, although the largest chunk of the gain actually comes from, in my opinion, the more interesting hands-off method of just these character counts. And for German, we in fact get over a 10% absolute accuracy boost, which is impressive. But based on Sprudela's question earlier, with Finnish, we see that the results are less pronounced. We still get a gain, but it's smaller. And one possible explanation for this is because English and Finnish are from different language families, they have less lexical similarity. That is, it's less common to have an example of an English word and its Finnish translation that are spelled similarly, which is what our model is trying to leverage. Okay. So also some qualitative results. This is actually the same table from before of the ones that the baseline got wrong, but I want to emphasize here that our model actually got them right. So it was able to look at these spelling hints and resolve these ambiguities. It's able to disambiguate these clusters from the word embeddings, leading to significant gains in the quality of these translations. And so to conclude this part of the talk, we can just see that yes, orthographic information can improve unsupervised bilingual lexicon induction, especially for language pairs with high lexical similarity, meaning that orthographic or spelling information is one possible way to get around the problem of not having access to parallel data. And with that, I'd like to move to the second part of the talk concerning machine translation, specifically in the context of translationese, which I'll define in just a few slides. So first of all, to recap, machine translation is like bilingual lexicon induction, but we'll be translating full sentences instead of words or short phrases from a source to target language. As an example, take Spanish to English. So like I talked about before, this would generally be trained with parallel data from Spanish to English. Pairs that look like this, a Spanish sentence paired with the English translation prepared by a human translator. Now, something I want to point out is that machine learning systems machine learning ultimately boils down to statistics and pattern recognition. And so your system will attempt to at least copy or emulate any common features that are shared by the examples that you train it on. So for machine translation, if you're using human translators to pair all of these, if there's something that they tend to do very often, your system will attempt to do that as well, which can be good and bad, and it depends on the quality of the examples, and it depends on whether these things the translators do are, for your purposes, intentional or not. And it turns out that there's actually something present in human translations that we don't like, and that's translationese. So translationese is a term that refers to artifacts present in translated text that are not present in text that was originally composed in that language. This can include things like simpler phrasing and interference from the source language. Now, translationese is present in human translations, and even professional translators will do this. And it's also especially present in machine translations because machine learning has a tendency to exacerbate these sorts of things. So I have an example. Take this German sentence. I won't attempt to pronounce it, but I will call your attention to 4 color-coded components of this sentence. That color coding is going to show where these components get translated to in each of two candidate English translations. The first of which I have labeled as more translationese, and this is the actual output from Google Translate at the time that this example was prepared. And it reads, the price of €20 for breakfast is under no circumstances authorized. There are two things here. First of all, in English, the euro symbol should come before the number, so that's just wrong. And also, this ending here is a bit clunky, under no circumstances authorized. And this example was actually shown to human raters who agreed that this was not very natural sounding. The one thing I want you to note about this is that this is actually a word-by-word translation. Looking at the color coding, you can see that these four components appear in the exact same order in both the English and the German, right? And this is what I mean by interference from the source language. So let's contrast that with another translation I've labeled less translationese. That reads, the price of €20 for breakfast is not authorized under any circumstances. So here, the euro symbol is in the correct position, and it's got a more natural, as judged by human raters, a more natural ending here, which is also exhibiting less interference from the German, because we had to take this German word, split it into a multi-word English phrase, and then put authorized in the middle of it, okay? So this is what I mean by translationese. So let's talk about it in the context of training machine translation systems. So we train our systems with parallel data prepared by human translators, which means that at least one side is going to be affected by translationese. Now, what do I mean by at least one side? So normally, if I want to do Spanish to English translation, I would take some Spanish sentences and pay someone to translate them into English, and then that English is translated, and so may have translationese. But suppose my friend wants to go the opposite direction, wants to go from English to Spanish. So they found some English sentences and paid someone to translate them into Spanish. For my purposes, I can take that data and just reverse it and train my model on it as well. But now the input Spanish potentially has translationese. And likewise, there are some data sets where a sentence was translated into two languages. And if I take those two translated languages and make a pair out of that, then both sides are translated. So all three of these types of data show up in modern translation training sets, but they don't distinguish them. And that's what this figure is showing, is this is for the parallel data, for the source and the target side of this data, whether each is original or translated. And so all examples have at least one side translated, and that's what we train on today. And specifically, if the source side is original, but the target was translated, we'll call that source original data. And if the target was instead original and the source was translated, that will be target original data. So again, training sets do not distinguish which example is of which type, but some test sets do. Now, why does this matter? Well, if you have translated text on the input, it could be too easy for the model to translate. Prior work has found that when you test models on inputs that are translated, they get inflated scores. You might think your model is doing better than it actually is, because in reality, your inputs are always going to be original. But likewise, in the other direction, human raters actually don't like seeing translationese in the output from machine translation. They can detect it and they don't like it. So we would like to train our models to be producing original outputs. So ideally, we would train our models on this quadrant where both the input and output are original, but it is completely unclear how to create data of that type. So what we chose to do is to frame this as a zero-shot task. We want to figure out how to train a model to translate from original to original, despite only having access to the wrong kind of parallel data, translated to original, translated to translated, and original to translated. Okay, so to do this, we're going to borrow a technique from multilingual NMT, NMT referring to neural machine translation. So a multilingual NMT model is just a combined model that supports translation between more than two languages. As an example, Google Translate system is like this. It has a single encoder and decoder that each handle all of the input and output languages respectively. But to control what to produce, they just have a reserved token that they prepend on the input. That basically means something like, please translate the following into English, or please translate the following into Korean. And with this, they were able to achieve zero-shot translation, by which I mean they were able to, for example, have their system translate from English to Korean, despite having zero examples of English to Korean parallel data. Perhaps it only had English to German and French to Korean parallel data. So we chose to treat translationese and original text as quote-unquote languages in an analogous setup, where we're just going to have this token at the beginning that distinguishes whether the target side is original or translated. But the problem that I mentioned before is that our training sets actually don't have those labels. So we don't already know the nature of the targets. So we trained a classifier to detect translationese in the target. But again, we don't have labels already, so how are we going to train this? We actually decided to use machine translation as a sort of proxy for human translationese. And we trained two types of classifiers. The first in this figure here is called a forward translation classifier. So we took, and for this we experimented with English to French, okay? So our monolingual target corpus would be French sentences. We show that to the classifier and say, hey, this is original French. And we also take monolingual English data, or source corpus, and use a baseline machine translation system to translate that into French and show that to the classifier and say, this is translated French, or translationese. And the other classifier is a round-trip translation classifier, where here we just have a monolingual French corpus. We show those to the model again, say, this is original French, but then under the hood, we round-trip translate it. We translate it into English, and then back into French, which in general will give you something a bit different than what you started with, and show that to the classifier and say, this is translated. So we tested both of these. The forward translation one ended up doing better, so those are the results I'll focus on for the upcoming slides. So what we did with this classifier was we used it to classify our machine translation training data. We looked at the target side, showed it to the classifier, and added a tag on the input based on whether it said the output was translationese or original. This is mirroring the setup in multilingual NMT systems. And because we have these tags at training time, at test time, we can pick which tag to give to the model, and we can tell the model to either produce more translationese or less translationese, or more original outputs. And we tested on two test sets. One that's source original, where the target was translated, and one that's target original, where instead the source was translated. And these are the blue results for that. So we evaluate MT with blue scores, which is we have a human translation and we look at our model's output and we see how close they are, okay? I won't spend a lot of time here. The main thing I want to point out, though, is that on the source original dataset, where the targets were translationese, if we told our model to produce translationese, it outperforms the baseline. And likewise, if the targets were instead original, if we tell our model to produce original text, it again outperforms the baseline. And this is interesting because our model and the baseline have the exact same architecture, the same number of parameters, and they were actually trained on the same data. The only difference is that for our model, we partitioned that data based on whether our classifier thought the output was translated or not. So that's cool. But if you remember, that's not actually what we wanted to do. What I said we want is to do zero-shot original to original translation. But there isn't any test data of this type, so we can't calculate a blue score. So what we did is we performed a human evaluation. So we took the source original dataset where the inputs are original, and we threw away the translationese targets. And we fed these through the baseline system and our own system, capturing both outputs from our system, the original and the translationese one. And we showed those to humans. We did two evaluations. The first was a fluency evaluation, where they were shown two, in this case, French outputs from different models and asked which one sounds like more natural French. And the other one is accuracy, where they would get shown the input and one output and asked to rate how accurate of a translation that is. So starting off with the fluency evaluation, in this table here, we compared the baseline, which had no notion of translationese, with our model when we asked it to produce less translationese, produce original outputs. And in this column, we see that a greater proportion of the raters preferred our model's output. But I want to contrast that with this blue column. These numbers are taken from a few slides ago, and they just illustrate that when we evaluate these outputs automatically against the translationese references that were paired with them, we actually get the opposite story, right? The baseline does better on this metric, despite in reality, humans prefer our model. And likewise, when we compare the two different outputs from our model, the more and less translationese, we get the same thing. Humans prefer the original outputs, despite blue score telling the opposite story. And also with our accuracy evaluation, we see something similar, which is that our original outputs are also rated as just being better translations. Again, despite the fact that using automatic metrics, they don't line up as well with the translated references that were provided, okay? So the conclusion to this, there's a couple parts. So first of all, It is possible to train a translationese classifier using machine translation as a proxy for human translationese. And you can use this to train a machine translation system to distinguish between translationese and original text. And when you do that, the system actually cares. When we changed what that tag was, there was a measurable difference in the nature of its output. And also, human evaluations show that it actually gets good performance in the zero-shot original to original setting, which is what we wanted. And finally, on these sorts of test sets, blue score, automatic evaluation, tells the wrong story. If this is all you do, you may end up selecting the model that's actually worse in reality. And so with that, I would like to move on to the third and final part of the talk concerning style transfer. So text style transfer is really the quintessential text rewriting task. We just want to change some attribute of the text and preserve the others. But when we call it style transfer, that usually means that the attribute we're changing is some aspect of style, which is very broadly defined. So I've got some examples. Style transfer could include dialect transfer. Suppose we wanted to change the British English, the lift in my flat isn't working, into the American English, the elevator in my apartment isn't working. Or for formality, we might change the informal I don't know into the formal I do not know. There are lots of potential applications for this type of thing, including grammar correction, localization, summarization, data augmentation, collaborative consistency, think like Wikipedia, making sure everything has the same style, and some others as well. So this is a very broad set of tasks. And specifically, we want to look at label-free or few-shot text style transfer. So parallel data for style transfer is very rare, right? But even non-parallel labeled data is scarce for many of the types of styles you'd like to transfer between. So as an example, suppose for formality transfer, it might be difficult to come up with a large data set where these are the sentences that we know are formal, and these are the sentences that we know are informal. So our goal was to train a style transfer model with a single unlabeled corpus. And we assume that it's pretty broad. We assume that it covers all the styles we care about, but we just don't know which sentence is from which style. Now, in order to do anything in this setting, we have to make an assumption. And the core assumption we make is that style is a slow-moving feature. And by that, I just mean that if we pick a random sentence from our data set, I don't know what style it's in, but I'm going to assume that the sentence preceding it has the same, or at least a very similar style. That's what I mean by slow moving. And that's what we're going to leverage during our training. So I'd like to talk a bit about the architecture for this model. I didn't talk about architecture before because in this project, the architecture is actually part of our contribution. So what we did is we fine-tuned T5, which is the text-to-text transfer transformer, which is just a large transformer-based language model that was pre-trained on a large amount of English web text. And our main contribution to this was to add in a style extractor, which is similar to an encoder. And what this does is it takes a sentence as input and produces as output a point in style space that we refer to as a style vector. So if you recall from before word embeddings, with word embeddings, we wanted to take a word and put it in some space such that similar words are close to each other. Here, we want our style extractor to put entire sentences into a multidimensional space such that sentences with similar styles are close to each other. And we also want this space to encode many different aspects of style. Now, the way we would train this is we sample two adjacent sentences from our dataset at each step. And the first one we'll call the context, and the second we'll call the input. The context we pass through the style extractor to get this style vector, this point in style space that the model should look to figure out what style the output should be in. And with the input, we're going to do what's called denoising autoencoding, which just means we're going to corrupt the input somehow and task the model with reversing that corruption, which requires the model to learn, to some extent, knowledge of, in this case, English to figure out how to fix it. And these tuning ranges on the right here, we use those as a way to give approximate guidance, hints to the model on how severe the corruption is. And the reason we do that is so that at test time, we can manually pick these ranges and control how much we want the model to change. Now, into this diagram, you see this corruption box, which I talked about a bit. We use two different types of corruption, primarily. The first we call noise, and this is where we just randomly drop, shuffle, or replace some of the input tokens. And that's actually what I'm showing on the slide here. Suppose our input sentence were, I really love it. This noise corruption might preserve really and it, but drop I and love, and replace one of them with this random other word, cat, okay? So that's the sort of garbled output that we get, and we task the model with recovering what we started with. The other type of corruption is more complicated. We call it noisy back translation. For this, as a first step for this, we apply that same noise I just described. So we get some garbled version of the sentence. And then we're going to take the model as it exists right now in training, whatever we have right now, and we're going to run it on this garbled sentence. What I mean is we're going to provide this garbled sentence as an input to the model and ask it to reconstruct what we started with, something fluent. But we're going to trick the model. And at this stage, we're going to provide it with the wrong context sentence, randomly sampled from elsewhere in our data set. And we're going to assume, with high probability, that should be of a different style. And so what the model should do is produce a coherent output, but it's in the wrong style. And so it's therefore different from what we started with. And this is crucial because that coherent but wrong styled sentence is the output of this corruption box. Okay, so it's not this garbled version here, it's something coherent, but in the incorrect style. And then we do what we did before. We provide that to the model with the actual preceding sentence and ask it to recover what we started with. Now, this is crucial because here, the examples the model is seeing, the input is a coherent sentence, and the output is too. The only difference is they're in different styles. And that's exactly what style transfer is. So this is how we are able to train our model to do style transfer despite not having any labels. Now, what do we do when we want to test this? We want to actually run the model at inference time. Well, we don't have the preceding sentence at test time. We don't even know what the output's going to be, let alone what's before it. So I mentioned this was label-free. It's actually few-shot in the sense that we do require a small number of labeled sentences that we call exemplars from both your source and target style, only required at test time. And what we're going to do with these, let's follow along in this diagram here. So suppose I want to transfer from style B to style A. I'm going to take all of my sentences from style A and independently run them through the style extractor, each producing a point in style space. And I'm going to average those. So I get a sort of quintessential average style A location. I'm going to do the same thing with style B. So I get these 2 points, and then I'm just going to subtract them, which gives us a delta or a direction in style space, representing the way you need to move to transfer from style B to style A. And then when we receive a test time input, we'll pass it through the style extractor as well. So this represents a point in style space where we already are. And then we're going to add that delta, that direction from before, representing the movement to do, representing a new point in style space that preserves the other attributes of the input, but has the style changed. And that's what we give to our model to ask it to, to guide it to produce the correct output. And we also provide the input as well to the encoder, and we manually pick some tuning ranges that we believe will be good for this type of style transfer. Now, how would we go about evaluating this? So first of all, we're going to specifically evaluate on sentiment transfer. This is between positive and negative sentiment. So for example, take a restaurant review. The service was great. Maybe we want to turn that into the service was too slow, okay? Now in this setting, there is no single right answer for what the model should produce. There are multiple correct answers. So we don't really want to do what we did for machine translation, where we calculate a BLEU score against human references. So we instead follow prior work. The first is called transfer accuracy. And this is just a measure of how often the model's output is in the correct style. So for sentiment, if we ask the model to turn something into positive sentiment, we then check, is the output actually positive? And we just measure this with a classifier. The second one is the other part of style transfer, representing content preservation, which is just, which you remember is just, you need to not change the attributes that you're not interested in, all right? And this is very difficult to accurately measure in an automatic way. So we just use a heuristic estimate in the form of self-BLEU, which is the BLEU score of the measure of how little the model actually changed, okay? Now I want to emphasize that these trade off with each other. So in order to correctly transfer the style, you need to change at least one of the words, which means it's impossible to get a perfect content preservation score. So we're really trying to balance this trade-off. We want to get the highest preservation score we can while also retaining decent accuracy. So here are some results. There's a lot going on here. Don't panic. I'm going to walk you through it. So on the y-axis here, we have sentiment transfer accuracy, how often the model produced something in positive or negative sentiment, depending on what we asked it to do. And on the x-axis, we have content preservation. This is a measure of how little the model changed. So in both cases, higher is better, which means on this grid, the upper right corner is where we would like to be. But remember, these metrics trade off with each other. So actually being precisely on the corner is impossible, okay? The next thing I want to draw your attention to is this green dotted line between these triangles. That represents our model. There are multiple points here because we have those tuning ranges. We can control how much we want the model to change. And so we tried various different values here. And we see that if we tell the model to change 50 to 70% of the input, it gets a really bad preservation score because it changes a lot, but it's very accurate at picking the correct style. And on the opposite end of the spectrum, if we tell the model to not change very much, it doesn't change very much, but is also unable to get good transfer accuracy. So in the middle, we can get a decent trade-off. Now, next, I'll call your attention to these blue diamonds. These represent models from prior work that is comparable to our own, and that they also assumed the same setting, where during training, you do not have access to labels. And we beat them. We outperformed these models, which is great. But I also call your attention to these orange X's. These represent models from prior work that were trained in an easier setting where they did have access to labels during training. And despite them having an easier task, we still outperform two of them and get quite close to the third. So because of this, we're very pleased with these results. But I also want to show some examples from our model. And for this, I want to emphasize something that is unique to our approach to this problem. Because we have this notion of a style space, and because it encodes many different aspects of style, we can perform style transfer for many different types of style without retraining our model. We can train one model that has this holistic view of style, and then we can control which style to change just by coming up with some additional exemplars, those examples. And for all of these I'm going to present, we had no more than 5 exemplars from the source and the target. So this is very easily doable by hand. So if we ask the model to just take a reserved sentence and make it more emotive, it does things like turn "I liked the movie" into "I cannot even describe how amazing this movie was" with 2 exclamation points. Going the opposite direction, "I loved every minute of the movie" turns into "I liked the movie." Also, for dialect transfer between American and British English, I had this example earlier in the talk, swapping elevator with lift and apartment with flat, and it can go the opposite direction as well. And what I want to emphasize here is that the model is not just memorizing certain words from the exemplars that we showed it, right? The examples of American and British that we showed to the model for these, in this case, did not include the words lift, elevator, flat, or apartment. They included distinctions like bar versus pub, and the word color spelled with and without a U. And it was able to generalize from that to do these sorts of changes, which is very cool. I'm going to skip the politeness stuff for time. Here's formality results. So making something less formal, we could turn "I hereby commit to never purchase anything from this institution in the future" into "I'm gonna never buy anything from this place again." Or for sentiment, turning negative into positive, take something like "I definitely won't buy this brand again" and make it positive. "I definitely won't hesitate to buy this brand again." And I like this example because it shows that the model is able to, understand how to change the input into a positive sentiment while preserving, in this case, all of the input and just adding 2 extra words. Finally, I have some additional examples here that don't correspond to the sort of standard definition of style transfer. We call these dialect-sensitive completions. So in these cases, the input to the model was of the form "my favorite something," food or hot drink, whatever, and a colon. We just ask the model to complete this in either American or British English. And when we ask the model to complete it in British English, for something like "my favorite food," it produces fish and chips. "My favorite hot drink," a mug of tea. And for American English, for "my favorite hot drink," it produces instead Starbucks coffee, right? And for for the band, the Beatles versus the Black Keys, etc. Right? So it's definitely learned something. It's perhaps stereotypical, but some aspects of American and British culture, the model is able to produce examples from them, distinctive examples. And also something I'll point out is that the input, we spelled favorite in the American way, and when we ask it to transfer into British, it actually changed the prompt by adding a U, which is kind of neat. And that concludes the third and final part of my talk. So the main takeaways for this part are style transfer is possible even if you only have a single unlabeled corpus. Also, our approach, our general purpose model, can handle many different types of style transfer without needing to retrain the model in between, which is of great practical significance. And finally, the model shows very promising generalization ability, which is exciting. So that concludes the final part. And so to just wrap it up, what I'm really trying to show here is that if you want to do a rewriting task from A to B, whatever A and B are, Spanish to English, formal to informal, whatever, you may not need parallel data from A to B. So on one hand, you might be able to make do with parallel data of the wrong type from A to C and from D to B. Or maybe you don't have parallel data, you just have non-parallel data for A and B. Or in the extreme case, maybe you just have data and you don't know what it is, but even then you can get some very striking results. And so with that, I'd like to thank everyone for your time, and I'm open to questions.